Hello, I'm here today with Charity Majors of the Parse division of Facebook. And this is a very different use case of MongoDB than we've seen in the class. So Charity, please tell us about Parse and what it does.
Parse is basically a mobile backend as a service. So if you're a mobile developer and you want to build an app, you can use Parse. We have SDKs for all the major platforms. We have a REST API, and we do core data storage. We do developer-defined analytics. We do push notifications. Basically everything that you need to build a really rich, fully featured mobile app without having to run your own backend servers or your own databases or your own API servers.
Okay, so let's say I wanted to create an iOS app.
Yep.
Right? I would open up Xcode. I'd create a new application. Yep. Maybe it's a multi-view application.
Yep.
And I wanted to store data persistently. And I was using Parse. How would that work?
Well, you would look at our data browser. It makes it look like a relational database. Basically, you can create what look like tables to you. They're MongoDB backed collections on the storage side. We also create certain sort of default collections for apps, like if you're going to send push notifications, you need to have an installation collection. Mm-hmm. So there are some collections that we create for you on the Parse backend side if you want to do certain things. You want to have installations or users or ACLs, or there's some things that we create implicitly. But besides that, you can create basically any type of collection that you want. You can define your own schema. You can define the data types, and you can perform. It almost looks like relational queries against them. And we at this point have over 500,000 apps on Parse.
Right. So it's a multi-tenant system.
Yes.
Where each of the apps is a tenant with all the other apps that are running on the servers.
Yeah.
So you said it was similar to relational, but from the end user's perspective, they can store data that's hierarchical as well, right? There's ways to put arrays and dictionaries
absolutely.
As values of keys.
Mm-hmm. Yeah, they can do online schema changes at any time, which is really nice. They can have a collection that has hundreds of millions of rows, and they can just decide to add another field in the data browser or in the brand new schema API. And we just do all of that magically on the back end for them. So
if a developer saves something to Parse to their developer account for that app, mm-hmm. using their API key, does it create a new collection behind the scenes, or is it commingle the data with other people's collections?
The collections are distinct, right? The UUID for the API key for each app is baked into the collection name, mm-hmm. so there will never be any collections that contain data from more than one app.
Okay.
Right. So you create a collection that's like the Andrew collection for your app.
Right.
It'll be like your UUID : Andrew. Which lets us, when you log in or when your app authenticate, you use your keys, right? So you only have access to the collections that are prefixed by your API key.
I see. And you also offer some, I looked at the docs a little bit, some higher level services for the users. It isn't just storing and retrieving data from MongoDB. There's some stuff for creating a new end user account, mm-hmm. and
absolutely.
Logging people in, and resetting their password.
Yep, absolutely. This was really the vision of Parse, right? For the founders, they started creating mobile apps themselves, and they're just like, why do we have to re-implement these very basic functions over and over and over again? This doesn't make any sense. This is tedious. We can make this a better experience for mobile developers. So yeah, we absolutely try to think really hard about what operations as a mobile developer do you find yourself just implementing over and over and over again, and how can we just bake them into the SDKs so that you have to write one line of code?
Right, that makes perfect sense. So when you do this behind the scenes, what does the architecture look like? Is it replicated? Is it sharded? What does it look like?
Sure. The short answer is it's very complicated. Our architecture diagram looks like spaghetti.
Okay.
But the very basic API request path is, so we run on AWS. So like we have an ELB endpoint that everyone accesses, api.parse.com. ELB talks to the web server, which talks to HA proxy, which talks to the API server, and which either talks directly to MongoDB or it talks to Cloud Code, which is the third party, which is the JavaScript server-side hosting service, basically. Cloud Code can also make return calls back into the API. And then the object is returned to the user, or the code, they can recurse many times. So, the basic API request path is just like your standard website path.
And you talked about Cloud Code. So, and this is an evolution, right? When Parse first started, you could store data and retrieve data, but you couldn't execute code on Parse servers.
Yeah, I mean, it's scary, right? Whenever you let people run arbitrary code on your servers,
right.
It's a little bit terrifying.
Right.
But it's been out there for almost 2 years now, so it's pretty solid. There are some restrictions like duration of time that the request is allowed to run. We do have longer running background jobs that will let you run like 15 minutes, but we restrict it to like 12 seconds for the basic Cloud Code API request, because fundamentally if it's running for longer than 12 seconds, it's a bad mobile experience.
Right. No, that makes sense. So with Cloud Code, what's the implementation language that the developer can use to
JavaScript. All JavaScript. It's a V8 engine.
And Parse itself, what language is it written in?
Fun story. When we started out, we were written in Ruby on Rails. There are many great things about Ruby. I personally love Ruby as a language, but it has this fundamental problem where you have a fixed pool of HTTP workers, right? And when you have one or two backends, maybe that isn't such a big deal because backends get slow. Problem with a fixed pool of workers, no matter what the language is that if any backend that they're all talking to gets slow, all of your workers fill up with requests to that backend, and the site goes down.
I see. Not good.
Not good. So we've just basically completed a 1.5 year long project to rewrite every element in our stack from Ruby to Go.
Interesting.
It's amazing. It's
wow.
Oh my God, it's been revolutionary for us. We love Go. We love the Go Mongo driver. I love Gustavo. I think it's the best driver that's out there. Our reliability has improved by over an order of magnitude since completing the rewrite, but it was hard, right? Because you're rewriting endpoint by endpoint, and it's really challenging to, and your mobile developers have baked in. Ruby is a very, let's call it, assumption-rich language. It makes a lot, it just like has default behaviors that you never explicitly specified. It just decided to do this. And we have been slowly discovering every single one of those over the last 18 months because as a platform, we cannot break this behavior for our developers. Maybe their mobile app hasn't been updated in 2 years. We can't break it.
Right.
We can't break any of these implicit assumptions. So we had to do this by, using a splitter, by shadowing production traffic, by moving endpoint after endpoint from the Ruby. We'd roll it out some percentage of time of requests from the Ruby stack to the Go stack and compare the results. Return the Ruby one to the developer, log any differences, and then go back and manually resolve those.
Oh, wow. That was a painful transition process.
Writes are one thing, rewrites are always harder than you think they will be.
It has to be bug compatible. If you
exactly,
will.
Bug compatible is a great way of putting that.
Yeah. So just to make it clear to the people watching, so and this is a complicated stack, right? So on your side, it was written in Ruby. Of course, the end developers who are writing Android apps and iOS apps were writing mostly in Java, Objective-C, or Swift.
Yep.
And they weren't exposed to any of that Ruby.
Yeah, no.
But the issue is that when they made requests to store data and retrieve data from Parse, they need to get back exactly the same results, regardless of whether your back end was written in Ruby or written in Go.
Yes.
Yeah. And so that's the challenge.
Yeah, and they'll bake in assumptions like, oh, well, this is totally going to return a null. Well, if you return an empty string, your app crashes. It's
right. Right. Details matter.
Yeah, details definitely matter.
So you said that you don't use sharding behind the scenes.
Correct.
You use, but you do use replication.
Yes, we definitely use replication. We use replica sets. We have a topology that is essentially, we started out using 3-node replica sets. We then so we started out in MongoDB 2.0, back in the bad old days of the global lock.
Okay.
Moving from 2.0 to 2.2 with a database level lock was really revolutionary for us.
Yeah.
And 2.4 and 2.6 have continued to, generally speaking, get better. But when we upgraded from 2.0 to 2.2, we kept encountering categories of bugs that would cause all secondaries to crash, which would leave us without a primary. So all requests would start failing. So we modified our topology to include 2 arbiters, right? This also had the ancillary benefit of making us more robust to availability zones going down, right? Because with the primary and 2 arbiters, we're alive, right? No matter what happens. If all the secondaries crash, if any AZ goes down.
So a primary, some secondaries, and 2 arbiters. It wasn't just the primary and 2 arbiters.
2 secondaries, 2 arbiters.
Okay, primary, 2 secondaries, and 2 arbiters.
And then we realized, because one of these nodes would be a snapshot node, right, where we do all of our backups.
All right, we'll get to that backups. Okay. Yeah.
Okay. And then we realized, okay, well, we don't actually want to be reading off the node that is serving backups because it will stall, right? It's a bad experience for our users. So we ended up adding, and also, if one secondary goes down, you're left with only one. If you have 2 secondaries and one goes down, you're left with only one, and that's actually not a great place to be in either, because you have to have a node taking backups. And in our drivers, we'll set things like prefer secondaries. We don't want to create roaming herds where all of the old secondary traffic is converging on the primary at the same time as maybe some other reliability event is going on. So we've actually moved to a model where we have the 2 arbiters, the 1 primary, 2 visible secondaries, and 1 hidden secondary.
All right.
Which has no votes and takes backups.
And we haven't talked a lot about that hidden secondaries in this class. But the goal for you is really, do you use the secondaries for some user traffic?
Yes, we do.
You do, right.
Yeah.
So
there are some read queries that are not efficient. In part, this is because there are some things that you just can't do with databases efficiently, and our customers do them anyway. Like we don't have code review for their queries. Sometimes they just implement things that do full table scans. They'll say, give me all the objects in this, 10 million item collection. We can't prohibit them from doing that. Or doing nested series of not equals to this, not equals to this. We try to tell people not to do that, but we can't really enforce it. They can still do bad things. So we try to automatically detect these inefficient queries and systematically rate limit them or offload them to secondary so that they don't impact everyone else on that tenant.
Okay. So that's actually a good segue, and we'll get back to how that works. Let's talk about indexing.
Yes.
Right? So the users of this service, do they create the indexes?
They have no idea the indexes exist.
They have no idea the indexes. So they write queries using a subset of the MongoDB query language that's been translated into the Parse API. Mm-hmm. So if they don't know if the indexes exist, how do you deal with indexing at all?
Well, there are basically 2 answers to this question, because we wrote one version of our smart indexing almost 3 years ago, and it worked really well for us for a while, and I'll tell you what that was, and then I'll tell you the ways that we found that it sort of fails and the new system that we're building. So the first version of smart indexing was basically computed on every single API request. We would look at the expected cardinality of the data type, like Booleans, not very indexable.
Right.
Strings, very indexable. And the operator type, right? Not equals to, not a great index, equals to is a great index, so we look at the operator type and the data type, and we would compute how valuable we thought this index would be, and we would ensure that the 3 best indexes for every API request existed. We would just create them inline. and like
the system would learn, basically.
We have a caching layer where it caches like which indexes are expected to exist. So this was the first implementation. There were some big problems with this and some small problems with this. One small problem was rate limiting index creation, right? Because you can do background indexing on primaries, and if the collections are small, it has super low impact on your performance. But obviously you couldn't do background indexing on secondaries for a long, long time, and you didn't want to build more than 1 index at a time per replica set. So we shifted from doing it inline in the API request to dropping them in a queue, right? And then using like Zookeeper to pick up a lock on we call them shards. They're not shards in the MongoDB sense, but it's like every app is coherent to a single replica set, right? So we wouldn't build more than 1 index at a time on a replica set. So this worked, like, honestly, pretty freaking well for a really long time. We did, just over the last year, we started to run into some pretty critical issues, though, where we turned on full query logging, like log level 1 for all queries, and we noticed that there are a few things.
So you get long-running queries. You'll see the long-running queries in the logs. You see all the queries in the logs.
We see all the queries in the logs, and we process them and ship them off to various magical Facebook logging systems where we can do real-time queries and what's going on. We can see things like lock percentage, nscan, et cetera, which helps us detect congestion with the multi-tenant setup. But for indexing, we were noticing that, number one, write performance degraded linearly with the number of indexes that were created for a collection.
Okay.
And since we were just creating all the indexes that we thought might be useful, performance is taking a hit.
Right, and what you mean by that is that any update or write needs to update every index.
Yep.
Right.
Yep. So if you have, 1 index, and you're only using that index, great. If you have 10, well, maybe you need all 10, but if you don't, you're taking the write hit anyway.
Yeah, you're taking the performance hit of increasing the latency.
And we have some users who would literally auto-generate their column names systematically, and they would run into the max is 64 indexes per collection for a very good reason, because that's way too many indexes to have in a collection, and their write performance would degrade, and then they couldn't create any new indexes, and performance would fall off a cliff. So we realized that what we needed was a way to detect which indexes were actually valuable and delete the rest, and not automatically create them on every single API request. What we needed basically was to create and maintain an indexing schema for every application, as well as a schema for every application.
So when you say automatically create them on every API request, you're saying that if the user made an API request and it didn't hit an index, then you would create the index right there?
We would just ensure that all of the 3 best indexes for every API request existed, period. So if you have predictable, consistent traffic, this is mostly okay. But if you go into the data browser and happen to click sort on a column, it's going to go and create that index. And maybe you never actually need that index, and you're paying the write performance forever.
Right. So you need to manage that.
Or you are doing a bunch of testing with your app, and you just send a bunch of wacky REST API requests. Well, we're going to index everything, right? Even though we may never hit those indexes again, we pay the write performance forever. So we've been developing a new system where we use the full query log to detect which indexes are actually valuable, which ones actually get hit, and we store those to an indexing schema. So we then reap the old ones that are not getting hit. This is also going to be really helpful for us. So I didn't mention this earlier, but Parse is really an outlier in terms of installations, MongoDB installations. on the axes of the number of collections that we have
Yeah.
and the number of indexes we have. Like, we don't have the largest Mongo deployment in the world,
Right.
but I'm pretty sure we have the most collections and the most indexes.
Right.
We're talking like tens of millions.
Right.
Which is very unusual. Like, there are lots of people out there who will have, there are people out there who have hundreds of shards. They have billions of records. We have billions of records. We have only 30 replica sets. We have an order of magnitude fewer replica sets than the largest installations that I know of, but like tens of orders of magnitudes more collections and indexes.
Yeah.
So this is really fun and interesting because we tend to find all of your query planner and index intersection bugs, because query planners are generally written for people who think about their indexes and manage them sanely. And we don't. We don't. We create them and manage them in a very automated, very insane way.
Yeah.
So there's lots of collisions. I'm pretty sure we found most of your greatest hits bugs for the 2.6 release, where the entire query planner was rewritten.
So, you have a system with, if I understand the architecture right, a replica set may hold holds multiple applications.
Anywhere from 1 to tens of thousands.
Now, how much of a problem is the noisy neighbor problem, which is that
Yes.
you're on a replica set, and you're unbeknownst to you, there's another application that's really, really popular, and it's just using all this capacity, and now you're not getting very good performance. Like,
it's been a really fun set of problems, for sure. So, and part of this problem is just the fact that mobile apps are unpredictable.
Yeah.
Someone will wake up and their app will be featured on the iTunes store overnight without them even knowing about it.
Right.
And they go from having a couple hundred users and their mom and their friends to having millions of users. This is one of the reasons that Parse is powerful, because we're used to solving these problems very naively at scale. We've seen it happen a million times. Not a million times. We've seen it happen many times. And we've gotten really good at automatically remediating these types of problems. So the greatest indicator of performance degradation in up to 3.0, up to the document level locking storage, is lock percentage, right? So we've put a lot of instrumentation into monitoring global lock percentages and database lock percentages, and automatically migrating around databases when they get too hot. If they're starting to cause co-tenancy issues. Now, every 1,000 apps that are created, we create a new database, basically. And this is kind of a dumb and somewhat arbitrary way. And I say dumb meaning like naive, not stupid.
Right.
Because it actually works really, really well, because it's incredibly rare that 2 apps in the same database will take off. And if they do, we have tooling to deal with that, but it's so vanishingly rare that it hasn't really been an issue. Much more frequently, the issue will be an app on a replica set takes off, and in the mmap storage engine, there's just the one global lock for some operations, and it can start starving its neighbors.
Yep.
So we detect that, and we migrate it. We've written some really interesting tooling. So it's really, really slow and hard to do Mongo dumps and Mongo restores. If you're trying to say, export an app from one replica set and import it into another, and you're going through that global lock, like it's hard, it's slow. If you're dealing with heavy write volume, you might actually never finish, right? So we wrote some kind of insane tooling. Asi told us it would be possible, and so we went off and did it. And she definitely did not tell us we should do it, but it's been kind of awesome. Basically, what we do is, if we decided to migrate, say, app data 376 from this replica set to this replica set, what we do is we fsync lock a secondary, rsync the data files to all members of the destination replica set.
Okay, so during this time, the secondary is falling behind because you're live migrating,
but it's hidden.
An app. No, I understand.
Yeah.
Right. So you have to live migrate an app without
fsync
skipping
lock
a beat.
it, rsync all the files, which
Right.
rsync is really fast. Like it is basically the fastest way to move data around. So we rsync the files, unlock it, tail the op log until it's caught up, and then flip all the apps in that database over to the new replica set.
Without missing a beat.
Without missing a beat.
So basically, at some point, you decide that it's caught up.
Yep.
And then the request can go to the new replica
Can go to the
set.
new place. Yeah.
Yeah.
And the thing about Mongo is it doesn't actually store a list of the databases that it thinks it has. It's just when you go and try to open app data 376, it looks to see if the data files exist, and if so, data's there.
Right. So one interesting implication of the way you've architected the system is that it turns out that even for large mobile apps, a well-built replica set can often handle the traffic without sharding. Because you're not allowing an app to be sharded.
So it really depends on the workload. Because we have all workload types, right? Like we have all different types of apps. There are apps that are read heavy, there are apps that are write heavy, apps that do nothing but game states, just save large game state blobs in the background. Right. Apps that do lots of geo queries, like if you name it, we've got it. And the reason that we started working with the RocksDB people at Facebook was because we found that scaling read queries was easy. Mm-hmm. Scaling writes, basically impossible. Now the canonical answer to this is we'll use sharding, right? So that you get multiple write locks. Mm-hmm. But managing the sharding infrastructure naively, like we tried this actually, we tried rolling this out last year, pretty expensive in terms of human cost, in terms of, you have to pick an intelligent shard key. Now imagine how important it is to pick an index. Right. Now it's very important. It's reasonably challenging if you're not familiar with backend systems. Now, picking a shard key that is useful and that your application can live with forever is like an order of magnitude harder, right? And once you've picked it, you can't change it. So this really goes against the entire Parse ethos of making everything magical for developers and creating a really beautiful developer experience where they don't have to be experts in backends, right? It's completely feasible for us to analyze their data and their requests and automatically generate a shard key, but then we would have to tell them they can never change it. They can never change, they have to issue the shard key with every single request, which means they can use a limited subset of our parse object model. It really wasn't working well for us. So we're like, okay, well, if the problem is the write lock, let's address the problem at the source, right? Mm-hmm. Which is why we started working with the RocksDB people. Now, RocksDB is probably the best write-optimized storage engine in the world. Mm-hmm. And we worked with you guys and Mark Callahan on the storage engine API. And Igor from Facebook has been working on plugging in RocksDB. Mm-hmm. There are a bunch of benchmarking blog posts on blog.parse.com, but basically we see 50x to 200x better write performance using RocksDB over mmap, which is insane. Like, how often do you even see these numbers in computer science? Right, no. It's like a leap of faith, So that's allowed us to scale up apps that are write heavy without having to deal with sharding.
Right. All right. So just to explain to people out there, so in MongoDB 3.0, right, there's a pluggable storage engine API that allows people to create their own storage engines. We ship WiredTiger along with mmap. mmap is the default, and you have a team that actually builds a separate storage engine called RocksDB, and you found that this offers 50x write performance over mmap.
At least. Up to 200.
Yeah, up to 200. That's
it's mind blowing.
Yeah.
So WiredTiger is also amazing. It's currently only the B-tree implementation that's shipped.
Right.
So you don't get you get the 10x compression, which is on par with RocksDB, but you don't get and you also get document level locking, but you don't get the massive improvements in terms of your write performance that you get with an LSM tree implementation. And I believe that that's coming for WiredTiger in 3.2.
Right. So, just to explain to folks, so these savings, there's always a trade-off, first of all.
Totally.
Writes are much faster in RocksDB.
Yep.
What's the trade-off? What does it cost?
Reads are a little slower.
Reads are a little slower.
Yeah.
Right.
Yeah, the median, the 50th percentile, a little slower. The 99th looks pretty good in comparison. But yeah, reads are a little slower across the board. This is a tax that we are totally willing to pay for our write-heavy replica sets.
Yeah, no, that makes sense. And regardless, it sounds like things get a little bit better for you in 3.0 anyway, right? Even with mmap, right? With collection level locking.
Yes.
At least in terms of maybe contention between applications. And then with WiredTiger, there is document level concurrency.
Yeah.
So that which you also get in Rocks.
Yeah.
Which means that all of a sudden now applications aren't interfering with each other as much, and
we can stress our hardware, like our really expensive database hardware. Like we can shift so much work from the lock
right.
to the hardware because you can do more things at once. So your throughput gets better. Like you're not wasting as much of that incredibly expensive, CPU.
You can scale
memory.
up on a box.
Yeah.
Not just scale out, but you can now scale up.
You can do a lot more work on a single node.
And especially for a system that doesn't want to shard for the end developer, being able to scale up a box is critical.
It's huge.
Right.
Yeah.
Right. So that's made a huge difference.
Yeah.
And it's fantastic that your team is working on Rocks.
Yeah. So the reason that we're super excited about WiredTiger too. Like Keith Bostic is like one of my personal heroes. Love it. Another reason that we started working with the RocksDB team was because we are so much of an outlier in terms of collections and indexes, right? And every other write-optimized storage engine out there, basically, and there's probably some reason for this that I don't know about, but they use a file per collection and a file per index, right? Well, we have so many of those, we started running into file system limitations and weird stuff. And the RocksDB team, they were like, we will personally solve your problems for you by creating column families. You can have up to 4 billion collections and indexes before you ever have to think about this problem again.
Yep.
So having a custom database engineering team in-house is kind of amazing. I recommend it to everyone if you ever get the chance.
If you have that luxury.
But like we wouldn't have it if we weren't at Facebook. So
no,
I can't exactly say this is a generalizable solution.
Yeah, but folks can use RocksDB. They can use WiredTiger.
Absolutely.
Yeah.
Yeah, we have a mailing list, Mongo-Rocks Google group. We're publishing, tarballs on a daily or weekly basis. We're going to be setting up dubs and RPMs. We really want to have more community adoption. We think it's, there's a huge commitment from Facebook to making this the best write-optimized storage engine in the world, period. It's going to be replacing all of the MySQL InnoDB stuff. Compression is amazing. So yeah, I think it's so good for the community to have storage options. It's simply a fact. It's like the speed of light. You can't optimize for everything at once. There will never be a storage engine winner that is the best option for every workload.
Right.
mmap is still better when it comes to reads. Better than WiredTiger, better than RocksDB. WiredTiger is great. It's going to be a great all-purpose storage engine. The B-tree implementation is going to be fast for reads, much faster for writes, and highly compressed.
Right.
And RocksDB, I think, is always going to be the best write-optimized storage engine and the best for people who have like an extreme number of collections and indexes.
Now, do you do any caching when someone's using their mobile app and it calls the Parse API to read data from Parse? Does it ever hit a cache, or does it always wind up hitting it?
For the most part, no, because we can't. Like this comes back to our naive approach to mobile apps. Like we don't know. For some apps, it's highly cacheable data. For some apps, they rely on real time. And this is a thing that we can't really detect just by looking at the query patterns.
You're talking about the coherency of the data. You're saying that if you cache it, there's a good chance that you...
Is there
if there are multiple copies, then
going to break, Yeah. Are they relying on real-time up-to-the-minute data? Now we've talked about, creating a caching product that will let developers set a, expiration time
Right.
on various fields. We haven't done it yet. I think it's a good idea. I would like to do it at some point. We do cache some things, like installation IDs almost never change. So we got a huge benefit from caching those and using memcache in front of Mongo for those.
Right.
But the things that we can't predict whether they're going to be cacheable or not, we don't cache them.
Okay. That makes sense. And you said that backups happen by f-syncing secondaries, basically.
EBS snapshot, because we run
EBS
completely in AWS. We f-sync, take an EBS snapshot of all of the rated volumes because we use provisioned IOPS, and then unlock.
You said you use provisioned IOPS, you don't use SSD-based
No,
nodes.
and the largest reason for that was the ease of the backup process, right? Like, EBS snapshots are really fast, really efficient. They only charge you for the differential blocks, so if you have made a lot of changes to a replica set, it's not going to take a completely new snapshot. They're really convenient. Now, that said, when we move to ROCs, we are moving away from provisioned IOPS because we've benchmarked PIOPS versus SSDs and found that we do get better performance. When we were using mmap, that wasn't the case. They were on par. When we were using mmap, we couldn't really stress the disks the way we can with document level locking and the newer versions. So we were just like, well, it's very convenient. It's a predictable workload. Provisioned IOPS gives you a predictable amount of IOPS. That's kind of the reason it exists.
Yep.
And the snapshots are really nice. So moving forward with ROCs, we've started rolling it out on the ephemeral SSDs and implementing our own LVM-based snapshot solution that backs up to S3.
Yep. And some of this stuff's kind of probably more detailed than we go into in this class in terms of production architectures and figuring out which storage engine you're going to use. That's really more in the DBA class in the ops related tracks.
Sure.
But it is interesting to hear a full story. So let's go back to the beginning. So Parse was actually acquired by Facebook, which is why people might be, when we're hearing this, might think, well, wait a second, this doesn't sound like my news feed.
Yeah.
And putting photos on Facebook. So it's obviously different. When you all started, and you were with Parse from the very beginning, or very close to the very beginning?
Pretty close.
Yeah. Why did you choose MongoDB versus other solutions back then?
It was the only thing that could get the job done, quite frankly, because we wanted to do so many crazy things. We wanted to offer such a flexible storage option for our developers. I mean, we can create indexes on the fly with Mongo, right?
Yep.
With MySQL, you have to think so much more upfront about what is your data going to look like, not just now, but like a year from now, 10 years from now, and you're stuck with those choices forever.
Right.
And at the time, like 4 years ago, Mongo was the only option out there. Obviously there's been so much activity in this space. There are a lot of storage options that are now trying to catch up to you guys. Your Rethink DBs, your Cockroach DBs,
Right.
And there's a lot of people who are chasing this space now. But at the time, Mongo was really the only player in this document database space.
It was an obvious choice.
It was an obvious choice. Rethink was around, but didn't have secondary indexes.
Yeah, so that's
that's
not going to work for you.
No, obviously. Having elections changed my life. I think 2.0 was when elections replica sets were introduced, so it was just kind of in the nick of time. But that is a killer story. That is a killer feature. I never want to get woken up again because some freaking primary went down. It's just unnecessary at this point in time.
And you exposed the MongoDB data model to your developers. They're to an extent. But I looked in your docs, I didn't see a lot of mentions of MongoDB. Are they conscious of the fact that when they make API calls to Parse to store and retrieve data, that there's some query going on in MongoDB to support each one, or are they?
It really depends on the level of sophistication of the developer. We have been out front and proud for many years as
No, no, right.
huge Mongo users.
Yeah, no,
but
certainly
we
everyone in the
don't want,
community.
like, one of the, main value adds of Parse is that as a developer, you don't have to think about these things. You don't have to know about it. Like, we're not, by and large, pitching to infrastructure savvy people. Our product is for making it easy and powerful to build mobile apps without having to think about that. So we don't spend a lot of time talking directly about the infrastructural choices that we've made behind the scenes,
Right.
Because it's not usually helpful for people.
Not
we
in the
don't,
spirit of Parse.
it's more like we want to make this native. We want to make it feel native to people who are used to spending their days in the, in the whatchamacallit for iOS. the coding thing that's not Vim.
Xcode?
Yeah, that one.
Xcode.
You can see which direction I'm coming from.
Yeah, no, I understand. Yeah.
I once tried to write a mobile app, and I spent the entire day trying to figure out how to do it in Vim, and then I just gave up.
That would be an interesting challenge on the Mac.
Yeah. No, I think that for our developers who are more savvy, if they're familiar with MongoDB, they can reason about what's happening behind the scenes more effectively. But we don't want that to be a prerequisite.
Right. And it is evolving now. If you wanted to just create a REST API with Parse and have all of the data access happen from there on your side, that's now possible as well.
Oh, yeah.
Yeah. All right. Well, thanks for coming here today. This is fantastic.
My pleasure.